All right, so welcome to IA215, automated work cell, and we've had a few lessons talking about how you set out the requirements and how you see how that work cell is going to fit in the overall business. And we talked a lot about motivations for why you do cells, and we're now going to talk about, now that you've got that first step done, you've got the cell basically laid out, you know what you're going to be replacing, you know kind of why you're replacing it, and you got target metrics that you want to achieve with your new automated work cell. How do you pick the right parts? So we call that component selection. And the purpose of the component, this particular video, is going to be to talk about the requirements, how we develop a requirements by component as part of the selection process. The second one we're going to go through is we're going to go through the entire component selection cycle, and then we're going to run through it, test it with an example. And then finally, we're going to just have some open discussion about how you make decisions stick, how you can get it so that when you pick a decision, make a decision about components, PLCs, robots, vision systems, that decision sticks and you don't have to go back and rethink it. So we're going to talk about building up that process. So we're going to go through the following steps. We're going to talk about the general approach. We'll go through the process. We'll start by looking back at the task map. That's our value stream thing, and the layout. And then we're going to talk a little bit about the human prototype, imagining a robot in your head, and then make your arm into the robot arm and test out your hypothesis on how it can work. Then we're going to start categorizing requirements. And those categorizing means where we decide we're going to slot our requirements in, which component does what thing. We're going to go get some quotes. We're going to talk about that a little bit. We're going to talk about the actual selection process, which is pretty much going to be looking at it from an analytical standpoint. We don't just want to randomly pick something because it feels good. We want to have a clear decision process with weighed criteria. So we're going to talk about one way of doing that. And then finally, we're going to talk about sticking decision, because sometimes you have somebody on your team or maybe your boss who, after you've made a decision, after you've had this part, maybe even you put down some money and it's going to be delivered soon, suddenly they're like, well, I really wanted that ABB robot. Sure, we shouldn't go back and get that ABB robot. I think we should. Let's order that one instead. And you've just wasted so much money and time that it's a pain. So we're going to talk about how we stick that decision. So I don't know if this is actually a quote from Voltaire, but it is a favorite quote of mine. Perfect is the enemy of good, especially when you're talking about a rapid prototype, when you're trying to just get something working quickly to see how it can be useful. Yet perfect is the enemy of good, which means we want to go fast and we don't want to achieve perfection right away. We want to get there through an iterative process. So the overall approach based on perfect is the enemy of good is speed is better than accuracy. And I don't mean the accuracy of the robot. I mean hitting the exact requirement set for the prototyping process. Speed is better. Being able to do things faster, testing out to make sure you can get the intent of the system, if not every possible criteria, is better than trying to get perfect. You also, in this process, you're trying to build a set of equipment to develop rapid prototyping so that your plant can test a lot of ideas quickly. Different machines to load, different things in terms of material to be packed and put off of conveyors into boxes or whatever you want a robot to do. You want to be able to develop the equipment needed to rapidly prototype that. You got to focus on small, fast, and have successes. And you never want to lose track of who is supporting you, the sponsors, the people who are going to give you the support you need on the plant floor or from the money, or the plant manager and the big bosses. You want to make sure that they're staying behind you. So you got to engage them as required, as they require. Some bosses want to be sent little notes on a daily basis. Other bosses will get really pissed if you do that. So you have to understand what they want. So you have to give them what they need, not what you think they need, and ask them. Wouldn't hurt. And it's also better to err on the side of over communicating. And also try to make them look good. I say inform and delight. Try to make them look good with some pretty pictures of what you're doing, little videos, things they can, send their boss and get a little ooh and ah out of. People love watching robots run. And finally, critical mass. The idea is you want to have, in the end, a set of equipment in your building where you've developed critical mass in the use of that equipment. Now, if in terms of a robot, that means you probably want 4 or 5 or 10 or 100 of the same kind of robots using the same set of spare parts and programming and support. That way you have that critical mass. You've taken the amount of money you need to support those robots and spread it across a lot of different robot systems. It will really save you a lot of money in the long run. So critical mass is an important concept. And always, and I mentioned this before, you have to balance the speed and the efficiency with the flexibility, how quickly can you change this robot to a different process with the cost. You have to balance those 3 factors and pick something that's going to meet those criteria. So what is the process? What is the process that we're going to run through to go from our task map, our requirement set that we had in this lovely value stream map and our layout, and convert that into a set of requirements so we can make a clear decision on our components. So this is a little process that I have used in the past. It is not the absolute best process, but it's worked. And so I would urge you to consider this as a process to go through when you're making selection decisions. And generally, we start right here at the top. You're going to start with the task map and the layout. The task map is right out of Lean. It's right out of how you want to improve your business. And we're creating a task map, a value stream map out of your new robotic cell. Then I suggest you do something called a human prototype. So you're going to have a human doing that thing. And so using the human prototype, you put yourself in the position of the robot, also the PLC. Obviously, the PLC doesn't have any physical movement associated, so you're not going to be moving your arm around, but you're going to imagine what each step that the PLC is going to need to handle. You're going to say, all right, I have a sensor here. And how is that sensor going to need to be dealt with? Well, that sensor turns on, we need to shut off the robot. Okay, do I have a direct connection between the sensor and the robot? Could I? Do I have enough I/O in the robot? So you put yourself in the position of deciding how you want to handle those conditions sitting in the place of the PLC. And you put yourself in the place of the vision system, and you put yourself in the place of the robot. The robot's the one that's the easiest to imagine because you move your arm around like a robot. So then as you put yourself in the place of each one of these components, you start to categorize your requirements. You say, all right, man, if I'm sitting in this PLC spot and I get a sensor reading saying, whoa, there is a conveyor that's moved over and the box is now in front of that sensor. And I'm like, I need to set that as a condition and then tell the robot next time it gets around to that step that there's a box ready for it when it gets to that step. So you're like, okay, all right, I could do that. And then you also realize by that you can't use the robot for that directly because that robot might be doing something else entirely while that little box is moving in front of that sensor. So I would need a special kind of code going on the robot where it's doing something in parallel, or I would use a PLC. And frankly, PLCs are an easier deal. And in general, I would suggest if you have a lot of that sort of parallel processing required, always use a PLC. The third area is get quotes. Categorizing means you decide if that sensor inputs go to the PLC or does it go to the robot. In this case, I would go to the PLC. After you've already gone through that, what you need to do is get quotes. And when we send out quotes, we've already started making decisions. We send out quote requests, rather. We've already started making decisions about these components. We've already looked up a couple of possible vendors. We've already looked at the vendor's, capability. So we know we've picked the right model of PLC or the right model of robot. And we're getting quotes in based on the requirement sets that we've created. In the case of a PLC, there's one set of requirements. In the robot, another one. After we go through that quote, we make a preliminary decision on a component or maybe two components. But then we don't end it there. What we do is we wrap back up to this top again and we say, all right, if we pick this component or these two components, what is my layout? Does it hit all my requirements correctly? And you test that again by prototyping yourself, checking your requirements to make sure you're categorizing them properly, and then re-quoting if necessary, and then make your next decision or finalize your decision. So this is kind of a loop that you keep looping through until all of your components are made based on a good decision process. So let's step through each one of these steps in a little bit more detail. First of all, we start off with what we call in the Lean Robotics book, the task map, which is really sort of the value stream view of our work cell. And we could see that we've got inputs. Inputs in this case might be some blank parts, some chunks of steel that are going to be machined and turned into a finished part. We've got information, data going into the process, data going out. We've got output. These chunks of steel now converted to finished parts are put into a tray. We've got our customers, we've got our KPIs, and we've got our total value added time that we want to achieve to hit our metrics. We also have our robotics layout. Right? From the layout, we can immediately get some critical data on that robot arm. We can get an idea of what envelope we need. And the envelope, then we can just grab a circle. We can add an envelope circle to our scenario here, and that circle would be centered on the robot. Actually, let me make this into a circle there. We can center that circle on the robot, and we can move that circle in until it hits all the things that robot needs to touch. And the robot needs to have plenty of room to touch the place where the part's put into the machine, 0.4 meters into the machine. We need to get both racks in that. And so this is the kind of circle that I might draw around a robot to get an idea of how that robot envelope needs to be configured. Actually, that's not centered on there. So I'd probably want to do this with a compass and center that circle right on there. And make sure that my trays are all in the range of the robot. And now I've got an idea of what that robot envelope needs to be. And it looks like, just based on scaling up the measurements in the picture, it looks like it's going to be right around 2-meter envelope. So 1 meter plus in each direction from the center point of that robot. Maybe 1.2 meters in each direction. So it gives us an idea of how to size the robot arm. And then as part of that robotic cell, we can start documenting what the final cell requirements are. What are our outputs? We start with the outputs. In other words, are they in a tray? Are they in a box? What are they? How much variety do you have for the parts that you're moving out of the cell? Are there 3 different shapes? Are there 18 different shapes? How much do they weigh on average each? So I know what my payload needs to be. So you have to document your outputs. We also have to document our target cycle time, because that will determine how fast this robot needs to run. It could be that a relatively slow robot is just fine. Like the cobot will be not quite as fast as the Yaskawa. It can be pretty quick, but doesn't quite have the full Yaskawa capacity and speed, especially at the payload that Yaskawa could handle. But if it's pretty close, it might be good enough. It's also less expensive and have less safety systems to deal with. So you have to look at your cycle times. We also have to look at our material inputs as well, because I have to pick up the slugs, these, cutoffs that are going to go into my milling machine. I have to pick them up. I might need a specialty gripper to do that. So I have to look at the range of different kind of parts going in. Are they coming in a tray? In which case I might know exactly where that tray is and I can go pick up the parts. Do I want to verify I have parts in the tray? Some way of putting the parts in front of a sensor to make sure there's really a part there and I didn't miss a part. All of these are inputs to the process. You need to document all that. We need to also talk about the movement overall. Each step in the manufacturing cycle in your work cell is going to have its own movement. The loads, obviously, we've already talked about that. What we didn't talk about is interface requirements. Are there overall interface requirements for the work cell to talk to some other type of system? And user interfaces and safety all are part of your overall cell. How do you want the user to interact with this? The user in this case is going to be feeding the robot, these blanks that they're going to be machining. So in this case that I'm using, the user interface is primarily a feeding and turning it on and turning it off. Is there more than that required? You need to document whatever it is. And then from that overall requirement set, the first thing you're going to do is choose and document your robot requirements. In the model that I just suggested there, we might have two end effectors. We might have one end effector to pick up the blank and then a separate end effector to pick up the finished part. So now I have the ability to change end effectors midway through the operation somehow. Or if I can choose a flexible end effector that's powerful enough to have sensitivity built in and the ability to check to see if a part's really there, such as the cobot end effectors, they've got the capability to know exactly how big the part is that they're picking up, because they're actually measuring the part as they pick it up, and determining whether a part's there or not as well. We have to calculate the payload for the robot. That should come straight from the cell requirements, and that would include the end effector and whatever component you're picking up. Obviously, the range of the robot, that's the envelope. I should say that envelope. The speed of the robot is going to be based on the cycle time. Reliability of the robot. Now, this is not so much of an issue for a large brand like Yaskawa or ABB or Universal Robot. These are well-respected brands with extremely high uptime expectations. It might become more of an issue if you're picking a low-end robot. And one of the videos I'm having you watch is a low-end robot vendor talking about how awesome their robots are compared to the other robots. And the reason why I picked that video is because I thought it was funny, and also because she actually does a decent job of explaining why you might choose one robot over another. So I really enjoyed her approach, if not her blatant sales approach. So it's fine. It's a good learning experience. And I'm not saying that her robot is not reliable, but her robot is definitely not one of the big brands, and you may want to consider carefully before selecting it. So the next area is maintenance requirements and training. Are you picking a robot that's one of in the plant? And it's going to require a lot of custom training. And now I'm going to have 2 or 3 people trained up to support that robot for different shifts and as backups for each other. And it's the only one out there. That's going to be really expensive for me to maintain training and spare parts for that robot. I may not want to do that. As well, the robot interfaces. If you have a robot that's a welding robot, you want that robot interfacing directly with your welder. And you can do it that way. So that way you can turn on exactly when you want it turned on, your welding torch, and can have communication for your torch temperature and that sort of thing. And then, of course, user terminal may or may not need a robot component there. Actually, let me take a user terminal out. That's kind of part of interfaces. The next component you start dropping in requirements on are PLCs. What is your total I/O count? How many digital inputs? How many digital outputs? How many analog inputs? How many analog outputs? PLCs can do things real time. Doing things real time with robots is more difficult in normal robot programming. Some robots allow you to program like a ladder logic like thing that runs in background. Like the Iskawas can do it. The Motoman used to be able to do it pretty well, but those are not easy places to do real-time programming, and there are limitations in that, especially limitations with I/O in the robots. So almost always you're better off taking anything real-time that has to be done real-time, check for, turn things on, turn things off, check for sensors, set up conditions. All that has to be done on a PLC. And safety systems as well. And many of your more complex safety systems, if there's a series of conditions that lead to a particular safety requirement, PLC is better at making those decisions. Most robots have excellent safety I/O associated with it, but if you have complex safety situations like this switch needs to be on, and this switch needs to be on, and this one needs to be off, and I can't have anybody within 20 feet, that's usually better off done in a PLC. Oh, the overall complexity of the work cell, a very simple work cell like the one we've been talking about, you don't need a big PLC. The little, Allen Bradley 850s are plenty big for a small work cell. In fact, they're probably plenty big for even a medium-sized work cell. And we're not going to go into the sizing process for PLC at this point. You're basically going to go to your vendor and ask them for that information. Also, I'll mention, is there a brand we always use? If there is, there's existing training, existing programming software, and spare parts. So we've already talked about that. That is a key factor. That's part of the critical mass of your business. You want that critical mass. Communication requirements are also important. If your little PLC needs to talk to an HMI, like the 850 can talk to the HMIs that came with it, those little Allen Bradley Rockwell HMIs, and it can actually talk to really big HMIs as well. That's something you might want. We also might have specialty interfaces. A lot of times you can extend a robot work cell by taking that robot, putting it on a conveyor. Then you've added another axis to that robot, a seventh axis that extends the range, extends the envelope of what that robot can reach. In fact, one of my first jobs, when I first got into robotics, way back in 1989, 88.
Careful now, Rob. You're showing your age.
Yeah, it's okay. I don't mind being old. I have lots of fun stories. I was designing a track system for a robot. And I took over after an older engineer who was helping them build it. And he was having them build this track system with this really crappy old gear motor with limit switches to control it. And I'm like, no, dude, you want to run this track with a servo motor. So I designed and built the track system with a servo motor with an old Mitsubishi robot on it. And we sold those a lot. But so yeah, you might have a specialty interface required for the PLC. In the case of a track system, that's actually something you can add in to some of the standard robots, like you can build in a additional servo axis to the Iskawas pretty easily as a custom build. Another area is HMI. Here in our lab, we're using these little bitty HMIs. We also have HMIs from Phoenix Contact, a little bit bigger. The reason why we're using the little Allen Bradley HMIs right now is because they came with the 850s and the software theoretically should all work together, but we're having some challenges there, aren't we? So I have to dive in and figure out exactly what's wrong there. Haven't done it yet. I'll do it before Monday. So the first thing we want to do with HMIs, human machine interface, is say, do we need an HMI? Do I need an HMI? Can I just have a push button that is basically start, and then maybe a big red button for an emergency stop, and another little red button for stop? So that way I can start the machine up and running, hit the big push button if I want an emergency stop, and that's all I need. Is that going to be enough? In some cases, it might be. It might be sufficient. I don't need to go get a fancy HMI. But if I do need to get an HMI, I need to say, all right, how many screens will I need to program? What kind of graphics do I need? Do I want to display a video? Do I want it to pop up additional information? You know, do I want to have it play some music? I'm not kidding. Sometimes they can play music. Do I want alarm enunciation? Do I want a history trend on there? Do I want all, et cetera, et cetera, et cetera? All those are potential requirements for an HMI. And then, of course, you have to make your decision about, is this something we have already in the shop? Should we pick something that we already have as our first choice because of that critical mass factor? And then last but not least, we got to talk about communication on the HMI as well. Chances are your HMI will be selected based on your PLC, and they will be designed to communicate with each other if you configure them properly. But you can't just choose an HMI without considering how it's going to talk to the PLC and the robot. And this is where we talk about who's going to hook to what. A lot of times the PLC is the center in terms of safety and interlocks to a work cell. And so the robot talks to the PLC, and then the PLC talks to the HMI, and the PLC might talk to your business systems through a Wi-Fi or Ethernet connection. Probably not Wi-Fi, probably Ethernet. So that HMI decision process is a critical part of what you're doing here. The next area we're going to talk about is the vision system. Overall, the first step we have to do is, what is the requirement of the vision system? Vision systems can do a lot of different things. When I first built my first robotic system, somewhere around 1990 or 89 or 88, it was a robotic system that picked up keys out of a shackle of keys. These shackles came in from these guys who will go out and use these keys to empty money boxes. And then they bring these shackle full of keys back. Literally, it's a lock with a whole bunch of keys on this big steel lock. They'd unlock that long steel shaft, and they'd slide all those keys into a little rack. And then the robot would pick the keys out of the rack one at a time, hold the key up to a vision system, and all the vision system had to do was read the key number. And based on the key number, the robot would then be able to figure out where to put that key back to. And believe me, since these keys were hand stamped and sort of randomly stamped and could get very dirty, and we had a lot of errors. It was a terrible thing. Plus, vision systems in the 80s are not what they are today. It was a Cognex vision system in the 80s. So vision system today can do a lot more than that. The ones we have in the lab are designed primarily for quality control. They're designed to look at images and decide if the image in the snapped picture that you just took is acceptable or not acceptable. So you have an original snap picture of the perfect product, and you compare that to the image you just took, and all right, is it the perfect product or not? Yes. I turn on an indicator to the PLC saying, yes, it's a good product. If it's a bad product, then I turn it off. And all this can be extremely fast. It can be so fast, like a bottling line with bottles flying by a camera with lights flashing, and so that the bottles flying by, knows exactly how to kick off the bottle if it turns out to be a bad bottle somehow. The cap's not on, the label's not straight. There's some junk in the bottle. So that's the second requirement. So the first one might be reading a label, getting a number off of it, or getting a barcode. The second requirement might be doing quality analysis. A third requirement might be locating an object. In other words, if I'm bringing a box full of objects in for that robot to go pick out of, I could have a vision system that could determine if that object that it's looking for is in that box. If so, where is it in that box and what is its orientation? And then the robot will learn how to go down and reach in, grab that object. Now, UTS obviously has one of these kind of vision systems for their robots for one of their packaging lines. It can know exactly what product has come down and what orientation. It'll reorient itself, grab that product, and pop it onto a little bin so that it can be packaged up as a variety pack. So that's a classic scenario for a vision system. Now that third criteria, that third situation is probably the most complex. If you hand a robot a pile of parts in any random orientation and you rely on the vision system to tell that robot exactly where it is and its orientation, that's the most complex thing. Now you need an expert in the vision system area as well as an expert in how the robot gets that data and applies that data and moves that data. So it's a very complex scenario. And there's more than that. You could have vision systems that do movement, checking to see if something's stable. You have vision systems that do analysis on vapors. You can have vision systems to do all sorts of things. Second thing with vision system is how fast. Are you in a bottling line where things are flying by 20 bottles a second? In which case you need a really fast vision system. Or is it something that you can go pretty slow on? And third, and probably most importantly for most plants, is it a vision system we're already using somewhere? Do we have the support for that vision system? And last but not certainly least, is the vision system to be able to talk to my robot and or my PLC? Is it going to talk through some sort of Ethernet connection, or is it going to talk through USB? Or more simply, is it just going to communicate through I/O? So that vision system is going to say, boom, I got a part of the wrong color. I've got the part of the wrong quality. Next time you pick up that part, chuck it into the box saying it's garbage. But it can go really slowly. All right, the next area is, we went through all the components now. We talked about how you would gather those requirements from your overall work cell requirements a little bit. So now we're going to talk about the actual comparison process for your different possibilities for each of these components. The first step is, if it's a no-brainer, don't overthink it. If you have 18 Allen Bradley Micrologic 1000s kicking around the plant, you might upgrade to a 1400 because thousands are obsolete, but you're going to still stay with the Micrologics brand in the right style that you want. It's the same style as your other PLCs in the plant. So it's a no-brainer. Don't overthink it. The second step is I'm just choosing the criteria. You have to choose the criteria for making your selection. Now, some of you guys already told me some of your core criteria, and two of them are pretty obvious. Cost. It has to be inexpensive compared to other options if all other factors are equal. If you're getting the same value of part, then you're going to choose based on cost. So to talk about that process, I'm going to pull up my spreadsheet. We're going to talk about how you would decide what are the criteria. And I'm going to go through some sample criteria. The next step is sending out quotes or sending out requests for quotations and reviewing those quotes as they come in. In fact, I forgot to mention setting out the RFQ in my PowerPoint presentation. And the last step would be doing the evaluation. And before I dive into setting these criterias, I need to talk about one thing. In almost every project I've ever been in, there's always been somebody, sometimes it's direct boss, sometimes it's the plant manager, sometimes it's the regional manager who just think he knows better than anybody else. He thinks that his decision for the PLC, for the robot, for the vision system, for the whole thing, maybe even he thinks that none of you guys should even be involved in this project. We should hand the whole thing off to a corporate group somewhere or to a vendor that he's getting a little kickback from. Whoop, I shouldn't say that. He's best buddies with a vendor somewhere. So you have to watch out for that process. How do you divert from that process and end up, how do you keep from having to use this boss's favorite toy that somebody's directed you to? There's no easy way to avoid that. If you have somebody like that in there, all you can do is line up all your sponsors and say, please don't make us pick something that we haven't selected based on valid criteria. Please don't do that. And throw your dice with your sponsors, because otherwise you're just going to get stuck with that VP's favorite toy that his buddy, his brother-in-law's son, does. So let's go through a selection criteria. So I'm going to share my screen I'm going to call this my sample component selection spreadsheet. Let's expand this a little bit here. So this is not that pretty a spreadsheet, but we're going to go through a little bit of a selection process as we go through this. It's a basic spreadsheet where each component option, you're going to say let's say we're going to do, this is the robot selection. Excuse me. Okay. So this one we'll do for the robot. Now you would do a same spreadsheet for a PLC and the same spreadsheet for the HMI if you have that as a separate criteria, or the vision system. Or you could kind of put them all on the same workbook, but I would keep them in separate sheets in that workbook. The first step you're going to go through is I would paste in the requirements you had straight from your previous exercise that cycle through your components, and you've picked out all the requirements for the robot. And I would just paste that information into your workbook without regard to the scoring criteria, just paste in here. So I would say paste in requirements. So paste that right in there. And then you're going to decide of those requirements, which one of them become selection criteria. So first one, it's an obvious no-brainer, might be payload, right? So your payload, you would say payload is equal to 2.5 kilograms. All right, so you know that your robot has to be able to, between the gripper and the part that it's picking up, that total payload is 2.5 kilograms. Or if you're in the real world, we'll call it 6 pounds. All right. Second is speed. We know we have to move that robot between point A and point B in a, we'll call it a 3 inches per second speed. All right. And how do you determine that speed? You become the robot and you, hey, all right, how fast do I need to move my arm between point A and point B to hit my criteria for cycle times? And you have your buddy time you, and you measure the distance, and that's your inches per second. Now it's average inches per second. The robot has ramp up and ramp down time. And it might depend a little whether it's a linear speed or an arcing speed. As you remember your robotics class, the robots go a little faster. If you put them in joint mode, they arc from position to position. There's less calculation required. But you get the idea. You just have an average speed. Third criteria might be programming. Do I have existing programming software how complex is the programming? Is it very complex programming? Is it very simple? Are there major decisions to be made? And this might be a complexity question. And what's another requirement? Actually, forgot the most important one, which is envelope. 2.5. Let's call it 2 meters. Actually, let's call it 7 foot total. 3.5 foot range. We'll call it 3.5 foot range. All right, so your envelope is probably another requirement. That's the range that the robot can reach. Another might be gripper. I need to have a 3-finger gripper with sensitivity. For instance, I mean, I can't think of an application where you really need a 3-finger gripper, but you might need a specialized gripper with sensitivity, or you might have the ability to do a gripper changeover. Though I don't think that the gripper has to be a criteria for the robot. But if you have an existing robot that is integrated with an existing gripper that does have, say, sense capability, like the UR robots, I'm using the UR as an example, then that becomes a criteria for your robot decision. And so you would add all your requirements in just like this. Now, in addition to those requirements, we're adding in some other scoring criteria. As far as I'm concerned, the requirements are either yes or no. So when we get to the scoring criteria, we start to weigh things. But when it comes to requirements, it's either going to be a yes or a no. It's not going to be yes, no. It's going to be a yes. And you're going to put in your robot, say robot A, UR. Payload is 6.3 pounds. We'll pick the bigger UR robot. The speed, it goes 5 inches per second, maximum speed. Its envelope is 4.5 feet. I don't know how much it is. And it can use any kind of gripper you want. Complex programming capability, yes. I can actually have multi-thread programming with my UR. Requirements, yes, met. Now, sometimes I like to highlight these. So if this column says yes, I make it green. And if it's no, I make it red. So now comes the scoring part, the part that's less clear in how it's going to work. In the scoring part, we go through how we want to score its value to our business. So, is this a robot that could help me in future projects? So if I need to change it out and move it to a different machine, how much value will that robot have for future use? And if it's a UR robot or a Scour robot, in general, it's going to be highly valuable for future use, assuming I have similar kind of machines in the plant that need to be loaded. So if it's like a one-off, I only have one of those kind of machines, and there's literally nothing in the plant that robot could be doing except for that one thing, it would get a score of 1 here. If it had future use where you had a lot of things, it would get a higher score. This is subjective. It doesn't have a hard answer. In the case of this, I'm going to say, yeah, there's a bunch of things I could use. Let's make all these centered here while I'm doing that. Right. Next one is flexible use. Can I have the same robot doing a whole bunch of different kind of applications? Yes, it's totally flexible. Next one is existing skills. Who in the plant already knows how to use this robot? Do I have programming skills? Do I have user skills to handle this particular kind of a robot? And if the answer is nobody in the plant's ever used this board, no one's ever seen it in training, no one's run across it in labs when they're working, getting their mechatronics degree, you get a 1 here. But assuming you already have a couple people in the plant who have that skill, it would get a 10. Existing maintenance support, same deal. Has anybody known how to repair one of these? Has anybody picked up a maintenance manual? Do we have anybody who's done any training? Have we swapped out the drive ever? Have we swapped out cables? The answer should be 10 if we have, and a 1 if you haven't. The last criteria is existing software. Do you have programming software available for communicating with that robot or programming the robot? If that robot doesn't need software, like I don't think the UR needs software, it comes with it. The answer would be you just take this criteria out. But if you're evaluating a PLC or an HMI, this is a very important criteria to load that in there. And you don't want to necessarily stop with these scoring criteria. You want to review these with your boss, with your sponsors, to make sure this decision sticks. So you're going to go through these and set the right criteria up with your bosses and with your sponsors to make sure this will stick. And then, of course, cost. Right? So then at the end of this, you're going to have cost and overall score. And your overall score is just going to be the average of these scores. In this case, just 7.25. And you might have a cost of your robot is $35,000. Guess we should turn this into a dollars thing. So the UR robot is $35,000. Its overall score is 7.25. Now let's go look at the Yaskawa. The Yaskawa might have a slightly higher payload, 7.2. All right. It might be able to go slightly faster, 6 inches per second. I mean, I'm just throwing this out. We'd have to look these up. It might have about the same envelope. I'll call it about the same envelope, 7.5 feet. Yes, it can handle a 3 gripper with sensor. Programming complexity, yes, it can handle pretty complex programming. So yes, it's going to meet requirements. All right. Future use score is about the same. Flexibility, about the same. Existing skills, maybe I don't have any Yaskawa programmers. Maybe it's only a 5 because I got one guy and he's, not available that often. I don't really like him anyway. All right. Existing maintenance support, maybe at the other plant. Existing software, we don't need any. And so my overall score is a 6.25. My cost for these guys is going to be slightly higher. So now we can see you've got a pretty clear decision that you can make there. Your scoring criteria is right there based on these requirements and these less than clear kind of judgmental things. You've got the cost and that overall score right there. Now, what if the Yaskawa ended up being super high? I had total flexible use. I got tons of skilled guys in my plant, men and women, all know what they're doing. And so even though it's slightly more, 42,000, my overall score is much higher. Now I might pick the Yaskawa because it's a better fit for my business and it gives me more flexibility. I've got more skills. I hit that critical mass. So this becomes your scoring criteria. That is how you go through this and make the decision. It's going to be a little bit subjective, and you're going to have to work with your team to come up with the criteria and how you do the score. It's going to be a little bit subjective. And in general, maybe a score 1 to 10 is too fine. It's really more like it sucks for us. It might be okay. It's awesome for us. Should be, either a 1 or a 5 or a 10. But some people like to make it more refined. So I always allow for the criteria of being 1 to 10 instead of, 0, 1, and 2, 0 being terrible. So this is a simple way of documenting a scoring process. Make sure that each of your components, your robots or your PLC, is going to hit your requirements. Make sure that you've got clear scoring criteria for those softer things that are also important for your business. And then you can make a clear decision based on that final result. So let's go back and talk about sticking to the decision. I didn't talk about sending out the RFQ, but sending out RFQs, usually guys like us aren't going to do. That's something that finance does usually, or purchasing. We'll send out RFQs for things they're going to buy. Basically, you just want to make sure you request a quote for the components that meet your criteria and that you've documented all the options that you need pretty clearly. Reviewing quotes is just a matter of picking out all those options. And if the vendor did not supply you exactly what you asked for and document it specifically the way you wanted it, then you have to have them requote. So my last slide for tonight, I call it sticking the decision. Plan for rethinkers. They want to rethink that process. Usually it might be related to the boss's favorite toy. It might be related to that. Sometimes, though, it's somebody in your team that got hurt feelings, that somebody says they didn't feel heard when they picked their favorite toy and all y'all didn't listen to them. So you got to plan for that. You got to assume someone's going to be disgruntled. So how do you plan for that? You communicate. You communicate with your sponsors, with your boss, with the purchasing department. Clearly the decision that you use for the criteria, and you communicate it broadly. You tell everybody decision criteria and the final decision reasons broadly. You also need to make sure that your team understands that once your team makes a decision about the system, you can't go out and start implementing a system and then telling everybody it sucks. You can't say, well, if only we picked another robot than this robot, it would be an awesome system, but these guys are going to totally screw it up. It's going to be awful. It'll never work right. Yeah, that's not a very good way of developing support from the rest of the plant on your system. So you have to make sure that everybody is good with that decision. And even if they're a little bit about things didn't go their way exactly, it still is important that they have that unified front. They support that decision. And also it helps to work with your vendors. As you reach out to your vendors, sometimes that final vendor demo to the plant manager, once you said you made that decision, they can bring in that robot or bring people to their location with a little dog and pony show. You can get the vendors to help stick that deal by demonstrating their unit and showing how well it works. And I'm talking about robots here more than PLCs. With PLCs, you generally don't have vendors giving you dog and pony shows for PLCs. They're going to just take your order, especially Rockwell, who really won't even be nice about taking your order. They'll just take your order if you beg them. But for robot vendors, they're often willing to do some demonstrations for you. So that is my roughly hour and 20-minute presentation on how you go through the component requirements gathering out of your value stream map, and then convert that into a decision process that then you can help stick your decision on.